In this video, I will show you the Gauss-Jordan elimination that's used for solving for a set of linear equations, a certain set of row operations to a matrix to make it reduced to its echelon form. I will show you the Gauss-Jordan elimination simply by going through an example, and hopefully this will be um, self-explanatory because instead of explaining what is done, I think the best way of showing the Gaussian elimination is to um, solve an example, actually. So this is actually uh, a, a presentation of methodology and an example. Um, to start, we have an ax equals b kind of linear equation like this, and then we would like eventually what we want to solve is x, the unknown, the xyz, the vector with xyz in it from this set of equations. And we would like to do something to this matrix A11, A12, A13, and all that, such that it changes into this form. If it were to change it into this form, identity, the unknown, and something on the other side. When we have that, we have our solution. If you look at this matrix multiplication, yeah, it is matrix multiplication. We know identity times any vector is the vector itself. But you can see that when we multiply xyz with the when we take the inner product of the first row and the xyz, we just take x, we just get x, and therefore C1 becomes x. And similarly, the second row is going to give only y, because 0 times x is going to be 0 plus 1 times y plus 0 times z. We're only going to get y equals C2, and the same for C3. So how do we convert the ax equals b form into some form that's identity, or it deserves a little bit asterisk on top of it, something that's very close to identity, as close as possible to the identity, so that makes us better analyze what's going on in this uh, equation. So I'm going to start with this example, right? So 2 minus 1, 3, 1, 2, 3, minus 1, minus 1, 1. And of course, I took this example, I designed this example such that the the row element operations, elementary row operations are easy to do, but the main idea is the same. So we will do only one of these three um, operations. We are allowed to swap the rows, it's easy, and we are allowed to multiply rows with a scalar, and we can add rows. So these are the three things, and we're going to do this to obtain the nice form that's going to make us solve for the system. And notice that in algebra, in high school algebra, we were actually doing it when we were given two equations or three equations. We were actually making summing them, multiplying one of them, to eliminate some of the variables and then go back to it and solve for it. But now this is a more systematic way of solving it. First thing that we need to do, we're going to make the leftmost element of row 1, this guy, to be 1. So I can either divide the first row by 2, but then I will have non-integer numbers. I don't want it to look so crowded. So what I'm doing is I'm going to swap R1 and R2. So if I swap R1 and R2, I would like you to notice one thing: I need to swap the other side as well. Notice how I'm not swapping the XYZ, that's there. And this makes sense because if you remember the matrix multiplication, inner product with every row corresponds to the output of that row. So if I'm swapping the rows, in order for the matrix multiplication to work through, I need to swap the output as well. So I do that. I swap my first row and second row. I get one, I'm one step closer to my Gauss-Jordan elimination, right? So one thing before I move on, and I will keep mentioning it and appending it to my ultimate solution, I can actually swap. There exists a matrix operation that when multiplied on the left with another matrix, it swaps the rows of this matrix or vector. So this operation, very simple here. This matrix that you see, 0, 1, 0, 1, 0, 0, 0, 0, 1. So this matrix is the one that swaps the first row and the second row. And it's almost very intuitive. It was going to be, so this matrix was going to be almost like an identity matrix, but there's only one difference from the identity matrix. It's that the first row is swapped with the second row, and that's the thing that I'm actually hoping to do, right? So why did I say this? Because this operation, I would like to express this operation, the thing that I did swap. It's easy to say in English. It's some descriptive action, but I would like for it to be a mathematical operation too. So on the top, so you'll keep seeing this same thing, and it's gonna get more and more crowded. I would like to show you that this is what I start with, and I when I multiply both sides with this, you see, this is the matrix that makes the first two rows swap, and I have to multiply the same thing again. So I know when I multiply, I know this two multiplication is the first row swapped, and similarly, it's going to be minus 1, 3, 0 when I multiply it with 2. So that said, the second thing that we need to do, add a multiple of the first row. That's why we made it 1. Add a multiple of the first row to row 2, so that the leftmost element of row 2 is 0. So this is the thing that I'm trying to lose in my next step. And how I do is I add negative 2 times R1 to R2, and I add it to R2. Notice how when I add a negative 2 times 1, it goes here, negative 2 times 2, negative 4, plus negative 1, I get 5, and so on and so forth. And notice how I do the same thing to the other side too. So again, the set of equation, it is the same. The row operations doesn't change my solution. It's conveying the same information. It is the same thing, but I'm solving it a little bit, little by little. And this operation, just like the one before that, this operation can be done with a matrix. And notice this one, again, almost looks like an identity matrix, but instead of the second row, instead of this being 0, I have it negative 2. So a little bit of smidge of the first row is added to the second row. So this operation makes the negative r negative 2 r1 plus r2 and return to r2. So again, you see the same thing. So this was my initial on the top. This was my initial matrix. So the matrix before this multiplication, and sorry, before this adding the rows, and I add this to the both sides, and I end up eliminating the second row, the first element, and you see on the bottom the whole picture, right? So as I keep appending, this third row is going to shrink, shrink, shrink. Like it's not shrink, it's going to get smaller and smaller because I will keep adding more and more matrix operations there. The third thing, again, using this one that I created, I would now love to eliminate this one. And I will keep moving forward, how I'm going to eliminate this one, I add a multiple of row 1 to row 3 such that the first element of the row 3 is 0, and I just add row 1 to row 3. Now it's becoming even more obvious. I just add 1 to this -1. This one becomes 0, and add the whole thing, right? 2 plus -1, it becomes 1. 3 plus 1 becomes 4, -1 plus 0 becomes -1, right? So I'm moving on. And again, there exists a matrix operation. It's like I'm adding the first row to the third row. You see it's almost going to be the identity matrix, but this one, if it weren't for this one, and this is the one that's adding the first row to the second row. And again, you see I already did these two element row operations depicted by these matrices, and this is my new operation. And notice how these things are getting um, multiplied on the side. So one thing that the thing that I'm trying to emphasize here by just crowding the screen here is that all of these elementary row operations are just linear matrix operations. Like there can be operators that do these operations, right? The next thing, now I used this guy to get rid of these guys. Remember what I'm doing, I'm making the A matrix as close as possible to the identity matrix. Now I'm going to use this guy to make this one 1. So how I'm going to make the second element of row 2 1, I'm going to swap the third and second row. How sneaky of me, because I could have if I had something like 2 here, I would have had to divide everything by -5, and I would have been dealing with like fractional numbers. I didn't want to deal with it yet, so I designed this example such that I can easily swap. I can easily obtain this by swapping the second row and third row. And notice how the operation that makes the swap is almost going to be an identity matrix, but the only difference is the second and third rows are swapped. So it's making the swap. And again, like I keep um, prepending the matrices that does this operation to the both sides. And as I move, so remember, this guy was my initial matrix, and this guy was my initial solution, like the other side, B, and this was my initial A. And adding all of these 4 matrices, I'm moving towards something that looks more close to the identity matrix. So I was here, I made this 1, and now I'm going to use this guy to 0 this guy. How I'm going to do it? A multiple of row 2 such that this gets eliminated. Of course, I'm going to add 5 times the row 2 to row 3 to get rid of this. And the easy way to do, and the matrix way to do that is to add this matrix, which is almost like a identity matrix, but this guy insinuates that the 5 times the row 2 has to be added to row 3, and I get this form almost like eliminated the one below the triangle diagonal matrix, which give us an upper triangular matrix. And so again, this simple new operations, notice how simple these little matrix multiplications are converting my otherwise difficult matrix. This is my difficult A matrix into a simpler matrix. Now I got an upper triangular matrix here. And I'm going to make the third element of row 3 to be 1, this guy, because I'm going to now move upward to clean up all of the other guys. And now I divide the third row by 17 to make this 1. And again, how sneaky of me, make this 0 such that I don't deal with 1 over 17 or any number over 17. And I can do that. The division with any row can be done with a matrix that almost looks like an identity matrix, except that row is 112, 117th. Okay, so now I get this form, this upper triangular form, and I get my diagonal to be 1. But sometimes I won't be able to get that form. Sometimes it is going to be such that when I do all of these eliminations, I will lose some of the elements on the diagonal. They're not going to stay. Uh, they're not going to stay 1. They're not going to exist. But in this example, they exist, and we call these elements ones on the main diagonal pivots. So we will. The pivots are important for us to understand certain properties of the matrix, which are going to become more important as we move on. But first, we got to pivots, and using these pivots, I'm going to go upward now, make them 0. And you guessed it, I'm going to use this guy to eliminate this and this. How do I do that? I add -4 times the third pivot to add it to the one above that and the one above that. So I can do this -4 and also this operation to eliminate. Yeah, I used this to eliminate this guy, and I'm going to use this one to eliminate this guy, and I'm going to then use this guy to eliminate this guy. And they can all be done with row operations. And now I was able to do the last operation, -3, R3 plus R1, and write it to R1, and voila. I get my diagonal matrix here. I have all zeros on the off diagonal, which makes my solution obvious here. So that made us that gave us the solution, which is x equals 1, y equals -1, and z equals 1. So when I have this form, there's a name for this form of a matrix when you reduce it, and it's called the reduced echelon form. And again, the reduced echelon form for all matrices are not always necessarily the identity matrix, right? Sometimes they are. It is going to look different sometimes, and I will cover that, and there will be implications. And finally, why did I show all of these element operations? So see, like we did 1, 2, 3, 4, 5, 6, 7, 8, 9 different elementary row operations to get this guy into the identity matrix. So if getting this guy to the identity matrix can be done with matrix multiplications, and multiplications of all of these matrices then has to be the inverse of this matrix. Why? Because A inverse times A is going to give me the identity matrix. And similarly, the same thing has to happen here, and therefore I can get x equals A inverse times the B. Now we got the solution without having to solve for the inverse, but actually we did solve for the inverse, but via element-wise operations. And this was the Gaussian elimination.